If a model returns embeddings, people often call it an encoder. If it translates, they call it encoder-decoder. Those habits are outdated. The same job can be served by different transformer designs. Encoder-only, encoder-decoder, and decoder-only are still useful labels, but they are no longer enough. I'm Mehrdad. In this lesson, we will learn a clearer way to read transformer architecture. Seeing embed, translate, or chat does not tell you which transformer design is running. Look at those three jobs more carefully. On the embed path, a causal QN3 model can still return an embedding from the final end-of-sequence hidden state. One translate setup is a model trained only for machine translation. An encoder reads the source, an autoregressive decoder writes the target, and cross-attention links them, as in NLLB. Another translate path, and the usual chat path, keeps one causal language model. The source sits in the prefix, and the answer is generated token by token. Same interface labels, different mechanisms. If this lesson is useful, like the video and subscribe for the rest of the Transformers and LLM Systems course. Put 4 systems on one board. QN3 embedding uses causal attention, a dual encoder retrieval setup, a contrastive vector objective, and an embedding interface. NLLB combines full self-attention in the encoder, causal self-attention in the decoder, and cross-attention for translation. Gemma 3 combines a vision encoder with a causal language model for multimodal generation. LLADA, or LADA, uses bidirectional masked prediction and iterative generation. All 4 use transformers, but one family label cannot describe them. The board separates 4 fields: attention pattern, system topology, objective and output head, and serving interface. Do not memorize every cell yet. We will unpack the mechanisms one at a time, then return to this same board and read it as an architecture specification. 3 attention patterns get mixed together in casual talk. Full self-attention lets every position look at the whole sequence. That pattern is common in text encoders and many vision models. Causal self-attention lets each position look only at earlier tokens and itself. That is the no-looking-ahead rule in most language models. Cross-attention is different. The queries come from one stream, while the keys and values come from another memory. A classic encoder-decoder system uses all 3, full self-attention in the decoder and cross-attention to connect them. These are composable patterns, not exclusive products. Video 5 covers attention scoring in more depth. For now, focus on where each pattern gets its information. Embeddings show why the old labels are not enough. Many embedding models use full self-attention, then pool the sequence into one vector. QN3 embedding takes a different path. It starts from a causal QN3 model, appends an end-of-sequence token, and uses that token's final hidden state as the embedding. Under a causal mask, that last token can still attend to everything before it. There is a second distinction that often causes confusion. Dual encoder and cross-encoder describe how queries and documents interact for search, not the attention pattern inside each tower. A dual encoder encodes the query and the document separately, then compares vectors. A cross-encoder reads the pair together and returns a match score for ranking. So ask 2 questions. What attention pattern sits inside the model, and how do the query and document interact? Translation makes the same point with topology. In NLLB, the encoder turns the source sentence into memory once. The decoder then generates the target token by token. Inside the decoder, causal self-attention looks back at tokens already written, and cross-attention reads the source memory. The decoder forms the queries. The encoder provides the keys and values. Another translate path keeps a single causal stack. Source text and instructions sit in the prefix, and the model continues left to right. Both paths generate the translation autoregressively. The difference is how the source is held: encoded memory plus cross-attention, or source tokens in the causal prefix. Translation is the task. The architecture can still be encoder-decoder or one causal stack. Multimodal systems make decoder-only an incomplete label. Gemma 3 still uses a decoder-only language model for text, but images first pass through a SIGLIP vision encoder. A projector maps those vision features into a fixed sequence of soft tokens the language model can read. Then those soft tokens and the text tokens share one sequence. Llama 4 is also autoregressive and uses early fusion, meaning image and text tokens meet in the language model input. Even with early fusion, a vision encoder still prepares the image before that join. So the full system has several parts: a modality encoder, a projector, a fusion point, and a language model that may be decoder-only. The language model is not the whole system. Video 8 covers multimodal representation in depth. For now, keep the parts distinct. Why did causal language models become the default for assistance? Not because only this design can do the job. The industry standardized around it. Next token training scales across large and diverse data. System messages, user turns, retrieved passages, tool calls, tool results, and answers can all share one serialized input style. Serving stacks then optimized for that style. Fast startup, KV caching, and batch decoding. None of those serving tricks are exclusive to decoder-only models. Encoder-decoder systems can use them too. But once tools, evaluation, post-training, and infrastructure all fit the causal path, switching costs rise. Causal assistants dominate through ecosystem convergence, not through exclusive capability. Generation is no longer only left-to-right next token prediction. LLADA, or LADA, was published at NeurIPS in 2025. Instead of always choosing the next token, LADA recovers masked tokens over several refinement steps, with bidirectional context. Dream 7B follows a similar masked diffusion idea and exposes a speed-quality trade-off. These models do not retire autoregressive assistance. Causal generation is still the production default, but causal masking is no longer the only way to define a generative language model. The live contrast is next token generation versus iterative refinement of a whole sequence. Return to the board as a checklist. Each row describes one system with 4 fields. First is attention pattern: full, causal, cross-attention, or masked bidirectional prediction. That field is a rule for information flow, not a family label. Second is topology: dual encoder, encoder-decoder, or a modality encoder joined to a language model. Third is objective and output head: contrastive vectors, sequence-to-sequence translation, next token prediction, or iterative denoising. Fourth is serving interface: embeddings, translation, multimodal generation, or step-by-step refinement. QN3 embedding, NLLB, Gemma 3, and LADA become readable when you fill those fields. Forcing them into one family tree creates confusion. Describing the composition is clearer. Next, we open the repeating transformer block at the center of these systems. If this Transformers and LLM Systems lesson was useful, subscribe to Multi-Agent Academy and connect with me on LinkedIn. Next, we open one transformer block and trace the residual stream, attention path, and feed-forward path inside it. Thank you for learning with me, and I'll see you in video 4.